when we talk about K, okay, because Le Chatelier's doesn't impact it. Only one piece, one stress of it will impact it. Guys, it's just a way that we write the equilibrium constant expression. Okay, it's kind of talking about what's happening. Is the forward reaction favored or is the reverse reaction favored? And that's what the K is going to tell us. All right, you can see it symbolized as a capital K or a capital K with a subscript EQ, meaning equilibrium constant, or a KC. They all mean the same thing. Okay, don't get confused with them. But very similarly to our delta H, does anybody remember the formula for delta H? Got to know it because you may have to calculate it. Heat of the products minus the heat of the reactants. Okay, it's always in that order, guys. Products minus reactants. So very similarly here with our K expressions are products over reactants. So this is a rate, so we're dividing instead of subtracting or anything like that. But it's the products over the reactants. And notice, guys, the coefficients, it's kind of hard to show it here, but really we should write it like this. So the concentration of my products and then my coefficient becomes a superscript. Okay, it becomes a superscript. The same thing with my reactants. Okay, concentration of reactants and any coefficients with those reactants go on top. So what this expression allows us to see very simply is, am I reacting in the forward direction more? So meaning the forward reaction is favored, or is the reverse reaction favored? So mathematically, if we take a look at it, if K equals 1, it means we're at equilibrium. Because your top and your bottom are equal to each other, so that should make sense to us. If K is less than 1, okay, meaning we have a small fraction, that means you have a bigger bottom, which means your reactants are favored if K is less than 1. Okay, more reactants. Less than 1, more reactants. If it's greater than 1, your products are favored, which means the forward reaction is going to be favored. So all we're going to do is just practice, guys, writing these expressions super quick, super easy, in case you see them in June. So here we go. We're going to write the equilibrium constant expression for N2 plus O2 yields 2NO. It's all gas. That doesn't... Oh, one other piece with it. I just glossed over something very important, guys. K only includes gases and aqueous solutions. Okay, liquids and solids do not have a concentration. Okay, remember that. They do not have a concentration. So, first thing you want to look at, do I have gases and aqueous? If I have those, then they're all going to be included. If not, I'm going to cross out solids and liquids because there's no concentration. This is the top of the next page in your notes. Top of the next page. So we're going to write K equals. Are we going to include all the reactants and products here? Yes, because they're gases, right? So they're all gases. They're going to be included. So let's go. It's products over reactants. So what we would write, guys, is the concentration. How many products do I have? No, just in general. 1, right? I've got nitrogen monoxide. So it's the concentration of nitrogen monoxide. But what else do I have to include with that? The coefficient. And that's going to become a subscript. So it's concentration of nitrogen monoxide squared over the concentration of nitrogen gas times oxygen gas. So if we were given numbers, like actual concentrations for these values, let's say this was 5, let's say this was 3, and let's say this was 4. We could then take those concentrations, guys, and we could plug them in to our equation, and we could actually get the K value and see which reaction is favored. So here we go. If we were to do that, this would be 4 squared divided by 5 times 3. So it would really be 16 over 15, which is not fun math. But you get the idea. It's going to be greater than 1, so my forward reaction would be favored. Alex.
How did you get 5, 3, and 4?
I just randomly picked those. I just made those up. Yep. You would have to be given the concentrations, like in the word problem, of saying, oh, it would be the concentration for nitrogen is this. I just made those numbers up right here just as an easy way to kind of do some easy math there. That's all that was. Is that your question? Yeah. So don't worry about that. That would be given to you. I don't anticipate you seeing it. I'm just showing you what you would have to do if you saw it. So I want you guys to try to go through A through E right now and write your K expression. No numbers, just the first piece that we wrote, setting it up like that. Letter A, guys, are all of those going to be included in our K expression? Absolutely. So K equals, it's going to be the concentration of CO2 squared divided by carbon monoxide squared times oxygen concentration. All right, that's what you should have for the first one. Letter B, are they all going to be included? No, so you're going to cross the ones out, guys, that won't be included. So really all this is going to be, for letter B, K equals the concentration of CO2. Now, you could write it as CO2 times 1 divided by 1, but those 1s would just cancel out and you wouldn't even worry about it. So if you have something, guys, that is a solid or a liquid, consider it to be just a 1, because 1 mathematically has no impact on a ratio or on a rate. Okay? So it doesn't harm us by doing that. Letter C, are they all going to be included there? Absolutely, they're all gases. So K equals SO3 squared, divided by SO2 concentration. Make sure you have the brackets. What do brackets mean or symbolize? Concentration, okay? We've talked about that, so make sure you remember that. Letter D, it's going to be K equals the concentration of HCl squared divided by concentration of hydrogen times the concentration of chlorine. Yeah, why do those have 2's there? They're diatomic, part of Brinkelhoff. And the last one, guys, as well, all of them are going to be included. NH3 gas squared all over nitrogen times hydrogen, cubed. Okay? Easy? Super easy. Again, I don't know if you'll see that or not. It's there as a tool, so you guys have it in your back pocket if you're asked to write the K expression. We'll see as we get into review. Acids, bases, and salts, guys, are the same thing. This is just a quick recap or review. When we did acids and bases, remember the formula? Some of you liked it, some of you didn't like it in the end. There's our KW formula. Guys, KW comes from this rate law. Okay? It would be hydrogen ion concentration times hydroxide ion concentration equaling that value. K equals that. So it's the same idea here where those values, where we could do the same thing. We would just cross out that. Our Ka means it's the rate constant for an acid. Kb is just for a base. You don't have to worry about writing this all in. Again, I don't think that you will see this at all. If we see it through our review, we'll go back and spend a little bit more time with it. But again, it's just showing how those are working in terms of the reaction that's taking place. So we're not even going to go through the rest of those. But Kw, it's this example down here where, we write this, Kw equals H plus. So that's where that's coming from. It's that equilibrium expression. That's where we're getting that K value, which is why I'm thinking, we're going to do equilibrium before acid-base next year. All right. Buffers, we don't need to worry about them much in this class. That's a college level thing, guys. But basically a buffer is a solution that can resist a change in pH. All right. Our blood is a buffer. We don't want the pH value in our blood to change because that could have drastic impacts, like death. Yep, pretty much. Okay. So that's the classic example of a buffered solution. The last thing we're going to talk about is entropy. Okay, the last thing we're going to talk about is entropy. We talked about it when you did your research. What is entropy? How do we define entropy?
Change of heat.
Hey, change of heat. Where's heat? Randomness. Or what? This should actually be an or. Or disorder. Or chaos, or messiness, guys. They all mean the same thing. So it's chaos in a system. All right? Nature tends to proceed toward a state of what? Higher entropy. The analogy, guys, that I used was like if you think about your bedroom, you clean it, does it stay that way? Okay? No matter how long you say, it's going to stay that way naturally, it takes work to keep it that way. My desk is another example of that. No matter how much I clean it, it just keeps getting messy and messy and messy. All right? So you can see that they tend to move toward higher entropy. Okay, higher entropy. So the more order you have, the what in terms of entropy? The less, right? It's kind of an inverse relationship. So the less order you have, the what in your entropy? Yeah, the higher, the more entropy you have. So when it comes to us looking at entropy in a system or in a reaction, guys, we're looking at the state of matter, or the phase change is the most significant. Okay? So phase change is going to be the most significant factor that's going to determine our change in entropy. Remember that triangle just means change. So going from solid to liquid to aqueous to gas equals what in terms of entropy, guys? So think about your states of matter. This is where your hands come into motion. Remember those hands that I taught you? Which state of matter has got the least entropy? Solid. Why? Because they stay together, they're very rigid, they're organized. Then you move into the gas, they start to flow around. But we didn't talk about aqueous solutions. Okay? In terms of aqueous, guys, why would aqueous have more entropy than liquid? What's the difference between liquid and aqueous? You should know this. What's that? Aqueous has ions, guys. Aqueous is a mixture. Liquid is a pure substance, but an aqueous solution is something else dissolved in it. So now you have ions, which that adds another piece to the puzzle, so you have more entropy, more chaos, and then obviously gases. So as you go from solid to gas, guys, you are increasing entropy. So if we draw our particle diagrams, something we've done several times before, we're going to continue to do it because you could see this and be asked to do that on your Regents exam, or that could be a way that you can explain something on your exam. So then liquids, all right, they kind of flow like this. And then aqueous, guys, they're going to look the same, but now you also have other pieces in there like Na+, Cl-, okay, that are in there as well, creating more disorder. So you've got another part added into it. And then gases, we know how I symbolize those with arrows. So they are constantly moving, all right, and they are spread way out, going any way that they want, filling any container. Now, in terms of reactions and breaking bonds and forming bonds, what do you think is going to happen, guys, when, in terms of entropy, when a compound is broken down, meaning bonds are broken, what's that going to do to the entropy?
Increase.
Why?
Because it's more disorderly.
Right, it's more disorder. They can spread out now. They're not being held together. So, guys, entropy is going to increase when a compound is broken down. You're releasing all that energy that's in the bonds. So then on the flip side, what's going to happen to entropy when the compound is created or formed? Yeah, chaos is going to go down because things are going to start coming together. Note, guys, if there's no phase change, you're going to count up the number of molecules on each side. Right? So this is kind of like if they're all gases, you're going to count up the number of moles, and which do you think is going to have more chaos? Yeah, the more molecules, the more chaos. All right, so if your number of moles goes down, entropy goes down, S will decrease, which equals a negative delta S. If the moles goes up, okay, should not be there, you can cross that out, means your S is going to increase, which means you have a positive delta S. Questions? Again, it's more ideas. You've got to just know it's not the math that's involved. So I want you guys to go through and tell me, is it a positive delta S or a negative delta S? Let's look at number one together. Number one, we go from solid to what? Solid and gas. So what's going to happen to our entropy, guys? Entropy is going to increase, which means our delta S is going to be positive. All right? So all you're going to do here with the rest of these is tell me, does entropy increase or decrease? That's all I'm looking for.